All right, so the write-ahead log. Uh, so the why, I guess I should explain the why of it first for people who don't know. So before, writes would come in and they would go straight into BoltDB. Um, Now, for the most part, this was okay, but occasionally Bolt has to resize the memory map, basically when the data gets bigger. Uh, basically every gigabyte that it grows, it has to resize the memory map, and that would essentially block writes um, when that was happening. So if writes are going directly into BoltDB and it's blocked while it's resizing the memory map, um, it would delay the write. So people would see sometimes write delays of like 3 seconds on up to like 10 seconds for larger databases. So basically what we wanted to do was decouple the write path with the actual storing of data in BoltDB, which is basically the indexed data store. Um, so the idea for the new implementation of the WAL was simply to write to files, to write compressed blocks into flat files. So basically, a write comes in. So say it looks something like this. Like here's a request which has CPU host equals A, value equals 23, some timestamp. Uh, you know, some other timestamp, and you just have a bunch of these down the line, right? Um, so what it does is it takes that write, uh, sends it to the engine dot write points, which in the BZ1 implementation, which is what we're using in 0.9.3, write points actually doesn't really do anything except for send it directly to the WAL write points. And what that will do uh, is the WAL consists of a number of partitions. By default, there are 5 partitions. And each partition is just a separate file that gets written to. So basically, it looks at the key for the series, which is this bit right here, CPU host A or CPU host B. It hashes that into a uint64, and then does mod number of partitions to find the partition it writes to. So the reason, so I'll cover why there are multiple partitions in a second, actually. So let's dig down into what a partition.write looks like. So essentially what it does is it compresses all the data using Snappy, then writes to current segment file, like log file. When it does this write, basically it says, is file greater than max size? If so, start a new file. Otherwise, then after that, do the write, which is the length of the compressed block, and then the block itself. And it just spools that all to the disk. After it does that, it does an fsync on it. So once you get a response from the WAL that write points has succeeded, it sends it on up the chain to engine.write points, and then the user will get a response back that the write succeeded. So once they've actually received a response that the write is good, they know that the data has actually been fsynced to disk, so it's durable. Now, the fact that there are 5 partitions means it's possible to get a partial write. It's possible for a write with multiple data points to be spread across multiple partitions. So what that means is, like, say you tried to write to, 3 different partitions, one of them succeeded and another one failed, the client would get a failure response, but actually part of the write succeeded. That's not that big of an issue because writes are basically idempotent, or they are idempotent as long as the clients are providing timestamps along with the writes. So they can just rebroadcast the write. But honestly, if a write to a partition fails, it's probably because of some critical system error that we won't be able to recover from. Either they filled up the hard drive or something very, very bad has happened. Okay, so by the way, if any of you have questions, please unmute yourselves and ask. Okay, so now the question is, why do we have multiple partitions?
Hi, Paul. You know it's me. I always have loads of questions. Always me. One question. You said that the whole point of the WAL was to, deal with these issues where when there was the mmap resized, there was a stall. I think I asked this before, but it's still not clear to me. I mean, at the end of the day, even with the WAL, we still have to write to both DB, obviously. So is this a matter of just reducing the number of mmaps? Because we resize, we still have to write to both at some point, so we'll still hit that problem. Is it just at a lower frequency?
It's not that it's a lower frequency, it just decouples the response time of a write from when that resizing happens.
Oh, I see. Okay, okay, cool.
So basically, the new write path, writes block for almost nothing. Like if you run a test, assuming that the index isn't overwhelmed, the variation you see in response time is very minimal. Like I ran a test writing 100 million data points on my laptop, and the absolute worst response time I got was, and this was 5,000 point batches, the absolute worst response time I got was like 860 milliseconds, and then the next one below that was in the low 600s, and the mean response time was 200 milliseconds.
I see.
Whereas before, the worst response time writing 100 million data points was 3.5 seconds.
Okay, perfect. That answers my question. Thank you.
And actually, for the 3.5 seconds thing, some people reporting worse times than that as the database got bigger, combined with the fact that if you're running on spinning disks, then the lag could be even worse versus running on SSDs. And the quality of the SSD matters, right? So, okay. So why the multiple partitions? So the reason I did that was because, so let me talk about the logic for when things get flushed from the WAL to bolt. So there are a couple of controls that you have. One is for each series, there's a marker that says when the series is ready for flushing. Our goal here is to get to a certain number of data points so they can be flushed in a compressed block altogether. So what we call the series ready size, right? And by default, this is, I think it's 20 kilobytes or something. Actually, this is actually exposed as the series ready size is exposed as an option in the config. So if you look at the config, you can see all these controls about when the WAL gets flushed are here in the config. So first, there's the WAL directory itself, which should be separate from the shard directory. There's whether logging is enabled. By default, this is true because the amount of log output that it produces is very little. It basically only outputs log information when a compaction or flush are running. The WAL ready series size, so this is just the number of bytes. So basically, if we do writes like and we just have a bunch of these, right? we collect all these together, and the data is basically keeps a map of series key to an array of bytes. And what those are basically just the timestamp and the actual encoded data. So once each of these is a specific data point in the series. Once the size of these points together reaches this, the ready series size, this series is marked as ready to flush, right? But it doesn't do it immediately. This is just something that tracks. So then the other ones are the compaction threshold, which is basically a percentage, like 50% by default, which means if we have a bunch of series in a partition, once 50% of those series reach this threshold, we can flush and compact this partition. So, and I'll get to what compaction means in a second. So then the other ones are the max series size, which is 2 megabytes by default. And this just says, if any series in the partition reaches this size, do a flush and compact. And then the max partition size, which is if all of the series in a partition reach this size, force a flush where you take the biggest series and flush them out and compact the rest. So the idea behind this is, I think this is 20 megabytes by default. The idea is this will keep the memory footprint down. So essentially, like, if you start filling up the partitions and it reaches this size, then it'll flush it automatically to start freeing up some memory, so it's not keeping as much in the cache. So this configuration option, more than anything, controls how much memory the wall will use. So doing a test on my laptop, doing the 100,000 series writes with this setting, I'm taking out the index from the equation completely. Influx ran at a steady state of 123 megabytes. So if they have less than if they have a gigabyte of memory on their server, this 20 megabytes is too high. But if they have a lot more memory, they can up this size so that they can keep more in the cache before they flush. And then the last thing is the flush cold timer, which is basically if a partition doesn't get a write in a certain amount of time, by default I think it's 5 minutes, flush all series in the partition. What that will do is 4 shards that become cold for writes, 5 minutes after they become cold for writes, they'll get flushed entirely, which will free up all of the memory that the cache was using. Okay, so those are the controls for flushing. The reason why there are 5 partitions for flushing and compacting is the idea is that not every series comes in at the same interval, right? You'll have some series that come in at once every 10 seconds, some series that come in once a minute, some series that are event-driven that may happen a few times a day. And the thing is, we didn't want to flush all of these at the same time because we wanted to optimize for series that had a lot of points together to flush all at once. So the idea behind a compaction is that we can do a flush and compact, and since we have 5 partitions, we would never be flushing and compacting more than 25% of the total space, the total series key space at a given time. And we're going to have to do more testing to see whether or not this is something we actually need at this point, because some of the other things in the underlying BZ1 implementation changed as as I was developing the wall. So some of the assumptions I had made actually may not prove to, like, maybe we don't need 5 partitions. But this works at the moment. We just need some perf testing to see what it looks like. But basically, if you have a bunch of series like this, if you have series, some that are regular, some that are irregular, and they have different sampling intervals, what you'll see when a compaction runs is we'll flush, say we'll flush 10,000 series, then another, say, 2,000 series in the partition get compacted into a new segment file in the wall. So basically they get kept in the wall until they hit this series ready size threshold, or they hit the flush cold timer. And the wall will actually give log output that says what type of flush is being done. If the flush is due to memory pressure, or the threshold being reached, or just that it was idle. It will tell you how many bytes are being flushed and how many series are actually being compacted. So remember, flushing is what gets sent to the Bolt database. Compacting is the series that get rewritten into a new wall segment file that gets stored. So what else can I say about the wall stuff? So the way the files work is...
Quick question, Paul, before you get too much further.
Sure.
You mentioned that we can tune the max partition size based on kind of the resident RAM to reduce the flush frequency. What's the advantage of that?
Fewer writes to BoltDB.
Okay, so every BoltDB write has a certain fixed cost, and it's better if we can slam in as much as possible each time we open them?
Yeah, well, because the way the BZ1 storage engine works is it keeps the data in compressed blocks. So if it's appending a new compressed block, that's really cheap. But if it's grabbing an old compressed block, it has to decompress it, add the points in, then sort the points if they need to be sorted, recompress, and then store it over again. So essentially, if we can minimize the number of write operations that we're doing to Bolt, it's better. It's better off.
Okay. Do you know if that relationship between match partition size and in-memory representation, is that roughly linear, or do we not know?
Not sure. We'd have to do some testing.
Okay.
I would guess it would be, but
yeah, I mean, we have people who are running with like 64 gig on the machine, so we should tell them to up that to like 200 meg, 500 meg.
Yeah, I mean, the biggest problem they're going to have right now is we're still building with Go 1.4. So if their heaps get too big, all of this data that's in the wall cache is actually data that's stored in the heap. So if their heaps get too big, they might see very large GC pauses. In theory, Go 1.5 will improve that, but we aren't. I think 0.9.4 is the first time we're actually going to maybe build with 1.5 and see. We're letting other people be the guinea pigs for now.
Right. Okay.
But that 20 megabytes to 1 gigabyte is just one sample point. It isn't that there's a 50. There isn't a that's well, 50 times bigger. That just happens to be.
Yeah, the thing that's not represented in that 20 megabytes, by the way, is the fact that there's the in-memory inverted index and the lookup map between the series key and the series. So if I had written, say, 100 million data points across 1,000 series, my memory footprint probably would have been much, much less than the gigabyte. Right. So the number of series affects the memory footprint almost more so than, say, the partition size, because for the partition size, when I'm looking at it, I'm only looking at the raw point data. I'm not also taking into account, all the other metadata that gets cached in memory as you're writing things in.
Okay.
Okay.
So basically, if people have a large number of series, like if you have 500,000 series, you are not going to be able to run on a machine with a couple gigs of memory. And anybody who has that expectation needs to really pray for a unicorn or a pony or a Pegasus maybe. because they have unrealistic expectations.
So I have a question. So I guess for example, if like partition 5 is getting flushed to the bolt DB, and then a new write comes in, and you do the hash calculation, and that's supposed to go to partition 5. How do you avoid the potential like long delay in response time, or is that going to have a long response time if the partition is actually flushing?
No, it doesn't. So the flushing is actually completely disconnected from writes going into the wall. So here's how the wall writes look. So here. So wall segment files. Basically, you have the partition ID, which is that. So here's what the sprintf string looks like, where it's partition ID and segment ID. So essentially, what that looks like is, so say we have partition 1 and 6. So that's the first wall file that gets created, right? Say that fills up, so we have a new wall file. This wall file is now read-only, basically. It will never get written to again. Not for writes. Right? So when a flush happens, flush comes in, we lock the partition, rotate the file. So now we do unlock partition. And then flush all files less than 3.
Quick question, Paul.
So what that means is we only block the partition for writes during this very short window of time where we rotate the file. So it's I mean, it's less than a millisecond.
Paul, quick question. I saw a user with a couple issues today, or actually I recreated an issue where I was getting a segment ID that was just 6 zeros. Is that expected or is that not correct?
Was that a meta file?
I mean, it was literally the output in the log was it couldn't access some WAL file, and it gave 122 as the bid and 6 zeros as the segment ID.
If it was a meta file, the first meta file is, I guess, 0 based.
Okay, maybe it wasn't. I don't know if it was meta or WAL. Okay, thanks.
So yeah, the other thing that I should mention is the WAL write points actually has a signature like this. I don't know why I'm typing this. So this is the signature of it. So you have the points, but then you also have the fields and the series that get created. So basically, when a write comes in, the TSDB store, the shard object actually, looks at the in-memory index and says which of these fields are new, which of these series are new. And then it hands this off to the engine write, which then just passes it off to the WAL write. So if there are new series or new fields being defined, what the WAL will do is it will write new series and fields to a meta file that looks kind of like that. And this is on a separate flush and compact timer than everything else. By default, it's once every 10 minutes. This data is already kept in memory anyway. The WAL doesn't keep it in memory. It just flushes it out to the file. Every 10 minutes, if that file is there, it'll rotate new meta file and write out to the engine, write out to Bolt. Also, on startup, it will flush any meta files in the WAL to the index. So, what does all this mean? So, one thing is that if you have this max partition size really, really large, it's possible for them to have a lot of data in the WAL that doesn't get flushed, which means if they restart their server, the restart could take a little bit of time, because when it starts up, it has to read all of the existing WAL files and load that data into memory. And like I said, because of the flush cold timer, generally that will only happen for whatever shard is hot for writes at that time. But if they have, say, a machine with 60 gigabytes of memory and they set this to be something very, very large, it is going to be slow to restart the server if they have to load gigabytes of data off disk to cache it in memory. What else?
If the server's loading up stuff that's cached from the WAL on restart, does the HTTP listener start before or after that WAL is flushed?
It should not start until after.
Okay. And when you say a while, I mean, we're talking this could be minutes?
I mean, if it's gigabytes of data, yeah, it could be minutes.
Okay.
So yeah, they don't want the WAL to get so big that it would take a really long time to restart. But if you're talking about hundreds of megabytes of data, it's, you know, tens of seconds.
Right. Okay. Thanks.
I think that's all I got.
The WAL you've just described, Paul, is that only for the BZ1 engine, or does it also kick? If I just happen to switch back to the B1 engine, I know we don't want to do that going forward, but would I still be using this WAL?
No, this is only for the BZ1 engine.
Okay.
Yeah. Is there anything I missed? Any other questions? No?
Actually, I have a question.
Yes.
So when you do compaction, you write the series that are not being compacted from this partition into like a compaction file, right?
Mm-hmm.
Could you not just also flush the series that are in that segment file as well? Because you're locking it anyway, so it seems like a lot of work to flush, like a lot of work to partially flush something when you could fully flush it, and it's probably going to be like just as expensive.
Like I said, the goal originally was to flush in like full blocks that could be compressed so that we wouldn't have to. So take the example where you have, like, let's say you have, you know, 50,000 series in a partition. And 40,000 of, let's say 10,000 have a sampling interval of every 10 seconds. And 40,000 have a sampling interval of once a minute. Or, sorry, 30,000. And another 10,000 have a sampling interval, like, it's like an event driven, so, or say it's like a sampling interval of once an hour. So normally when you do a flush, most of the time what you'd be flushing is 10K unique IDs, right? Which in Bolt essentially look like 10,000 random inserts in the key space, because the key space is bucket and then the time, where the bucket is the series key. So this is the way it works now, right? It would flush those 10K, compact the other 40K. And then every once in a while, it would flush 40,000, which are the 10-second ones and the 1-minute ones, right? And again, you're talking about 40,000 inserts in the key space, like random inserts in the key space. And then, once in a much greater while, it would flush the full 50,000. Now, if we just flushed all of them all the time, what would happen is most of the time we'd be flushing 40K, and then sometimes we'd be flushing 50K. So it's basically the difference between doing frequent, 10,000 inserts per flush versus the other thing. Now, if every single one of your series is sampled at the exact same interval, then all of this none of this applies, right? Because then you're flushing them all at the same time. But based on conversations I've had with people, it's very common for people to have different sampling intervals for different series. So this was an optimization. Doing the compaction instead of flushing everything all at once was an optimization to try and reduce the number of inserts into bolt at a time. Does that make sense?
Yeah, that makes sense.
And the truth is, we'd actually have to do more testing to see whether or not it actually is a gain. At the time, I don't know what I was thinking at the time. I think it was I wanted to get a collection of data points that would be one compressed block that would get put into bolt. So basically, if I could write, 1,000 points in one go in one insert, then that was much better than doing, 100 points in 10 inserts. Yeah, the goal really was just to lower the number of actual writes that are going into bolt, because it's not a write-optimized data store, right? It's a read-optimized data store.
Okay, I think that answers it for me.
Anything else?